Welcome to this explainer. Okay, if you're staring down the barrel of your S5 Microcontrollers Module exam right now, you are absolutely in the right place. Today, we're going to put away those heavy textbooks and just discover the high-yield, purely exam-oriented topics together. We're going to lock in the core definitions and those big concepts that are practically guaranteed to show up on your test.
I know the syllabus can look massive. The acronyms are essentially a total alphabet soup, and time is seriously ticking. But listen, we can break this all down into a highly focused, totally test-driven roadmap. The goal here is to help you walk into that exam room with total confidence. So let's dive right in.
Here's our game plan for this session. First, we'll do an intro to embedded systems. Second, we'll answer what is a microcontroller. Third, decoding ARM and Cortex-M. Fourth, RISC architecture basics. And finally, fifth, we'll hit those crucial Cortex-M features.
All right, Section 1, Intro to Embedded Systems. This is our macro view. Okay, so if your professor hits you with a short answer question asking for a pure definition, here is exactly what you need to remember. An embedded system is a specialized computer system designed to perform a specific function within a larger mechanical or electrical system. Now, the absolute key words you want to drill into your brain are specialized and specific function. Unlike your laptop, which is just a general-purpose computer that can run games, web browsers, and word processors all at the same time, an embedded system has a dedicated single job, and it's often operating under very strict real-time constraints. Just think of the anti-lock braking system in a car. Its one and only job is to stop the wheels from locking up, and it has to do it instantly, right? Now, this concept almost always translates into one of those classic 5-point exam questions. If they ask you to list the characteristics of embedded systems, you're going to want to quickly jot down these 5 points. 1. Single functionality. Think of a calculator doing only math. 2. Real-time operation. This means it absolutely must respond to events within a strict time frame, kind of like an airbag deploying. 3. Low power consumption, which is super vital since a lot of these run on tiny batteries. 4. Compact size, because obviously they need to actually fit inside other devices. And 5. Cost effective. We have to keep those production costs down for mass manufacturing.
Moving right along to Section 2. What is a microcontroller? We're zooming in on the brains of the operation here.
A really crucial concept to lock down is that a microcontroller is a compact, integrated circuit designed to perform specific, control-oriented tasks. But here is the defining characteristic, the part that totally separates it from a standard microprocessor. It contains the CPU, the memory, so things like RAM and ROM, and the input-output ports, all integrated onto a single chip. While a standard microprocessor usually needs external memory and peripheral chips scattered around a motherboard to even function, a microcontroller brings the whole team together under one single roof.
If you have to draw or visualize a microcontroller's architecture for an exam illustration, I want you to mentally photograph this setup. Start with your CPU smack in the center. Then, draw connections outward to the RAM, the ROM, the I/O ports, and your peripherals, like the ADC, the DAC, and the clock. But the big defining trait you absolutely must highlight to get full marks is that all of these components are housed within that one single compact microcontroller package.
Let's hit Section 3, Decoding ARM and Cortex-M. It is time to clear up that acronym soup.
This is a massive aha moment for a lot of students. Let's map out the exact hierarchy you need to know. ARM is the company, right? They're the architecture designer. They draw up the blueprints. Cortex-M is one specific family of 32-bit processor cores designed by ARM, and they are specifically optimized for microcontrollers. And then finally, STM32 refers to the actual physical microcontrollers manufactured by companies like STMicroelectronics that actually use those Cortex-M cores inside them. So just think of it like this. ARM is the architect, Cortex-M is the blueprint for the engine, and STM32 is the final car rolling off the assembly line. So, where are we actually using these Cortex-M processors out in the wild? If you get an application-based question, you want to group these real-world examples together. Because they so perfectly balance performance, power efficiency, and cost, these 32-bit cores are basically the absolute go-to for IoT or Internet of Things devices. They're in wearable health monitors because of their low power draw, and you'll find them in automotive safety systems, drone controllers, and robotics because of their incredibly fast, deterministic real-time processing capabilities. Definitely have these examples ready to go.
Which brings us to Section 4, RISC architecture basics. Let's look under the hood at the engine itself. First things first, RISC. RISC. That stands for Reduced Instruction Set Computer.
You really don't want to make a silly spelling mistake and lose easy points here. Cortex-M processors are based entirely on this RISC architecture.
But what does reduced actually mean in this context? Well, it definitely doesn't mean the architecture is somehow less capable. It just means it uses a small, highly optimized set of simple, fixed-length instructions. Because the instructions are so simple and uniform, it is much easier for the processor to decode and execute them. This drastically reduces the complexity of the hardware itself and vastly improves the overall execution efficiency and speed. Simply put, simpler instructions mean a much faster, more efficient engine.
All right, final stretch, Section 5, Crucial Cortex-M Features. These are your high-probability test topics.
Let's rapid fire through these vital features because professors love testing on this. The entire Cortex-M family is anchored to one thing: efficiency. First up is low power consumption, which is supported by dedicated sleep and low power modes. This is exactly what allows battery-powered embedded devices, like your smartwatch, to run for days without charging. Second is fast interrupt handling and deterministic real-time behavior. In a real-time system, when an event happens, like a sensor suddenly detecting a crash, the processor absolutely must stop what it's doing and respond immediately, every single time without fail.
And speaking of fast interrupts, I'm going to give you the ultimate secret weapon keyword for your exam: NVIC. That stands for Nested Vector Interrupt Controller. If you see any question asking how Cortex-M processors handle multitasking or fast interrupt responses, NVIC is the exact answer you must write down. The NVIC is this advanced controller built right into the processor that manages priorities. So if a critical hardware error pops up while the processor is in the middle of doing a routine calculation, the NVIC instantly pauses that math, handles the critical error based on its high priority, and then seamlessly jumps right back to the math. It's basically the ultimate traffic cop for the CPU.
To wrap up the technical side, let's quickly trace how this architecture actually evolved across its different generations. The ARM v6-M architecture, which includes the M0 and M1, was all about simple, low-cost, low-power applications. Then came ARM v7-M, bringing higher performance for things like heavy industrial control, with the M3, M4, and M7. But the one you really need to highlight for modern tests is the ARM v8-M architecture. As more and more devices got connected to the internet, cyber attacks became a massive threat. So ARM v8-M introduced built-in hardware security features. We're talking about ARM Trust Zone technology, found in the Cortex-M23 and M33, to actively protect sensitive data and support secure firmware updates.
All right, let's leave off with a final application question that you very well might see on your exam. Which Cortex-M processor architecture would you choose for a highly secure IoT device that requires real protection against cyber attacks? Think back to those hardware security features we literally just explored. You now have the exact definitions, the visual layouts, and those key distinguishing features down cold. You are completely prepared, you're focused, and you are absolutely ready to crush this exam. Good luck out there.